Hello everyone, I'm Steve Smith from Atlassian, and welcome to Knowledge to Power and Understanding Git. So the background of this talk is to give you a bit of insight into what Git is doing underneath the hood. It's going to walk you through some of the base principles of Git to understand its internal model, and then show you how you can use that internal model to fix problems for you in the real world. This is more of an intermediate to advanced level talk. If you're brand new to Git, it might be a bit rushing far ahead, but then it doesn't hurt either. So how many people here were at Devoxx last year? How many people tried to attend a talk called Practical Continuous Deployment? Oh, there's a few, sorry about that. I got me and a bowl of stooflies disagreed, and I had severe food poisoning. This year, I've been exceedingly smart. I've done the right thing. I've eaten nothing but frites and the finest Belgian beer since yesterday, so I should be fine this time around. Admittedly, my tongue is now burnt, so I've got a hangover, but we'll try and get through this, shall we? So, you'll hear the following a lot. This is from the Git book. Git is fundamentally a content-addressable file system with a VCS layer on top. This is true. You also hear a lot of stuff about acyclic graphs. Don't worry, it's an acyclic graph. It's really, really simple. Unfortunately, if you're learning Git and actually trying to get work done, not a case of I'm trying to learn Git fundamentals, I'm trying to learn I want to get my job done on a day-to-day basis, this isn't a hell of a lot of use to you. Sarah Jane Hodgkin-Westby, who spoke at Git Merge this year, a really great conference. I recommend it. It's all up on the web. You want to go and check it out. It's a great talk about how to learn Git at a high level, how to teach Git at a high level. It drives her nuts because you're telling people, oh, it's just easy. It's just an acyclic graph. Like it's giving her, massive headache because people are just getting confused. They want to do task-based learning. They want to go, okay, I'm starting a new branch. Why am I starting a branch? What's the point? Okay, I see. How do we do a push, a pull, the rest? What's the high-level model? How do I get work done? However, that will work up to a certain point. Unfortunately, it tends to break down once you start getting into some serious work. Once you start trying out things, or even just your team gets bigger, or you try out more complex workflows. Sarah Jane gives these tutorials and talks about how to learn Git at a high level. This is not that talk. This is the other talk. This is the talk you have behind closed doors when all the shit's hit the fan, and you've got to realize this is how it actually gets done. And that's where you get somebody else who actually has learned the low-level model, try and teach it to you. Ideally, we'd like to learn that beforehand, which is hopefully what this talk will be giving you the power to do. So I assume everybody saw this XKCD a few weeks ago. This is actually really, really good. It's explained, this is a kind of, everyone's had this experience with Git. It's, what you do is you find some magic commands and they work for you for a while, and then you screw up and you realize, oh, I can actually just pull it all again, so I'll do that. You don't even try fixing it. However, you sometimes get into a situation where you do need to fix it. If you follow the secret text, the alt text for that, you'll have seen this text as well. It's talked about a friend, that magic phone number, that person who knows how Git actually works and can tell you what the magic commands are to get you out of trouble. This talk will hopefully get you a step closer to being that person. Because here's a secret. That person doesn't actually know those commands. He doesn't know half the command set of Git. The command set of Git is not really important. It's the internal model. Once you realize the internal model, you realize what commands must exist in that universe. You can work from first principles and work out what needs to be done. Even if you don't know the commands in question, you can go, well, I would like to do this, and so there's almost certainly a command to do that. So we'll take you through a few of these commands today, but we will also be showing you how to think like those commands, how you could even implement those commands yourself. So with that, let's dive right in. Let's go to Git internals. This is a broken down or a blown out model of the Carlsberg Brewery in Amsterdam. No, it's not. It's in Copenhagen. What am I talking about? Anyway, it's a brewery, which I do like them. So the first level of the Git model and the fundamental level on which all other abstract concepts are built is the blob. Now, this is a bit of a slightly scary video, but don't worry too much. The blob is actually exceedingly simple. So the blobs actually can encapsulate a bunch of things. And this is, by the way, if you look at this now, this is Git. That's the lot. That's it. And we'll talk you through that as we go. So there are only really three types of objects inside Git. There is the content blobs. There are trees, which point to content blobs. These are very conceptually similar to file systems. And then there are commits, which point to trees, which point to objects. Commits give you a changing model over time. But this is basically it. I'm going to actually show you this at a very, very simple, low level. So let's have a closer look at this in action. This is down at the file system level. So we're going to do a git init. That creates a new empty Git repository. And then we're going to do a tree. Tree is just a Unix command that does a recursive ls of commersive directory show through the whole thing, through the whole directory. As you can see here, there are simply two directories inside Git objects. There are other stuff in that Git repository file system on your local file system, but it's basically, I'm just going to show you the objects for now. So there's info and there's pack and nothing else. So that's because there's nothing in the repository. It's an empty repository. Let's put something in there. We're going to put an empty file. So touch is a Unix command that will either update the file stamp of a file, or timestamp of a file, sorry, or it will create an empty file if none exists. So this is an empty file. And then we do a git add. That's merely telling Git, track this. It doesn't actually create a commit, it doesn't put it into the history yet, but it says, I want you to track this now. I want you to keep your eyes on this. So we've added it into the Git repository in a very shallow way. So as we look in these objects again, we can now know there's a single Git object in there. Now it's broken down into subtrees. So what it does is it takes the first two numbers of the hash and uses that, and then it puts it into different directories. That spreads the load out over the whole directory. Rather than having one directory with potentially millions of files in it, you spread them out a bit more evenly. But just stop there for a second. What is in that file? Well, theoretically nothing because it's an empty file, but there's actually data in there. So what a blob is at the Git level is a header is added to the file, to the contents. The whole lot is zlib compressed, and then a hash is taken, a SHA-1 hash. That's the lot. You could implement this stuff in half a day, the low-level stuff of Git, very, very easily indeed. All you need to do is a couple of libraries that do SHA-1 hashes, zlibs, and that's pretty much it. So we've added the file, and it's got a hash. So we've added a header, and we've taken a hash of that file, and we've used that to identify the file. Now, of course, if this header is always the same, which it must be because Git is essentially a standard, and the content is always the same, that hash is always going to be the same. This is what we talk about by a content addressable file system. Anywhere in the known universe where the same laws of physics and maths apply, an empty file will always produce that hash anywhere. If I had 15, 20, 1,000 files into Git that are all empty, they will always return a single file. That's it. That's what a content addressable file system is. So that's that concept. But of course, just adding files with hashes, without names, without any other information is not a huge amount of use. So we're going to do a commit. We've added a file. We say, now Git, I want you to keep a track of this. We want you to track it over time. The commit gives us that step. It creates the first in a chain of changing information, changing content over time. So let's do that. So let's do git commit with a message, and that's it. So let's have a look at that object tree again. So the tree again. Now there are 3 objects. I talked about there are 3 fundamental object types in Git. These are the 3 object types. One is the blob. that is, we add it. It has the same hash, always will do, because it has the same content. We also now have a tree. The tree points to the blob. It says, it gives it the additional metadata. Obviously, talking about hashes isn't an awful lot of use to us. We want to talk about them in a higher level. We want to talk about file names. We want to talk about permissions on files and track those as well. That's where the tree comes in. The tree points to objects. It can also point to other trees. So you've got a hierarchical file structure. It contains metadata around the authors, around the files, around the timestamps. It contains data around the permissions. So Git will track all of this for you. So that gives you the file system. That gives you a name can be associated with a blob. So for instance, I talked about adding a whole load of empty files to this, and you always end up with the same blob. So you can add 1,000 empty files, but Git will only ever store one blob. But if you want to give those 1,000 files 1,000 names, there's going to be 1,000 entries in your tree, metadata. So you've got metadata built on top of data. Now we want metadata over time, of course. We want to store commits and changing trees and changing objects over time. So this is where the commit comes in. So there's 3 objects in the tree because there are 3 blobs. There are 3 types of metadata. One is the content. The other is the tree that points to it and says it has the name. It identifies that by the hash, and associates a name with it, and a bunch of other metadata that looks a hell of a lot like a normal Unix-type file system, which is not surprising because it was basically written by a file systems and Unix person. And on top of that, we have a commit that says this, at this time, this author created this tree, and it points to the tree by its hash, and has a bunch of other metadata. And it's fairly free-form. You can add other metadata in there, and we will do in a bit. I'll show you some stuff that gets added later on. Of course, a single snapshot in time is not a lot of use. It's a version control system. It's a change system, change control system. Therefore, we want things to change over time. And that is where the idea of chains of commits come in. And this is how we build our high-level abstractions in Git. There is a fundamental chain. We start with our first one. That has no parent. But the next one has a parent and points to the one behind it. So it always points backwards, never forwards. So it's kind of like a linked list. It's a link. You start at the beginning, and you can find the next one each step along the way. But you're coming from the start, from the far end. So you're always going backwards in time. This is basically how you change it in time. If you if you add a new file and create a new tree that points to that new file, you have a new tree. That tree has a commit associated with it, and the commit may have a parent associated with it to tell it where it came from, how it got to that state. So from this, we build the fundamental building blocks of Git. So let's look at something else. We're going to actually modify this file that we created before, same file. We're going to add some content to it. And what happens? Well, we have an entirely new blob. This is back to this idea of content addressable file system. Any change, a single byte, a single bit inside a file results in a completely different object because it is a different content conceptually. It has a different hash. This is, what we're talking about, content addressable file system. Now, this may seem a bit inefficient. If you've got a gigabyte file and you change one bit in it, you're going to have another gigabyte file. This is one reason why Git is obviously not that great at large file systems, which one of the things that Atlassian and GitHub are working on together. But it's also one of the fundamental insights of Git, and I'll talk a bit about how we deal with some of these inefficiencies. But let's go one step up the conceptual tree. And talk about how we address this as humans. So far, I've talked almost entirely about hashes. We have file names inside trees, but we can't really get into those trees because the trees have hashes, and we actually talk about hashes. Hashes are not a great thing for humans. So we need something that operates at a slightly higher level, something that is talks to in a human way about the objects and points in time and commits that we are talking about. And this is where refs come in. So refs are the next level up, and they're exceedingly simple. A ref is just a pointer to an object. End of story. In fact, at its simplest level, it is just a file with a string in it that contains the hash of the object it's pointing to. That's the simplest form of ref. But we don't generally deal with refs very much directly. You can do, but you're operating at a lower level then. It's kind of fun to do, it's good to know, but you don't actually want to operate them. Generally speaking, you're operating at a slightly higher level of abstraction. So we're talking about the levels of abstraction. Even if you don't know any of what I'm talking about here, you will probably have come across. The first one being is a branch. Branch is one of the fundamental concepts of Git, very important and a large part of its power. One half of its most powerful concept of branching and merging and doing so in a consistently and cheap way. So a branch is just a commit that has a parent but does not follow the mainstream. Or to put it another way, a branch can be seen as an object which actually has two children. So because we talk about parents, the commit only points back to the previous commit. There's no reason why you can have a bunch of commits that all point back to the same one. And these are branches at its simplest level. This is why branching is so fast. All it is we're talking about creating new commits that have a different or shared parent in them. The reason they become very simple, the reason we can use them is because we associate a ref with them. We call it a branch. So a branch is just a point of divergence and a tag associated with that, a ref associated with that says, okay, we're going to talk about this branch, this stream of development as my feature or whatever. The other one you've probably come across is a tag. A tag at its simplest level is exactly the same thing. It just, by convention, doesn't change over time. That's it. It's just a reference that has a name associated with it, and it just points at a commit, and unlike branches and unlike the mainstream of development, that reference is not updated. Of course, talk about branches and so on. Obviously, all the branches have refs associated with them, including your default one, which is usually master, and any tags will can point to any objects in the history of the tree. Now, of course, because these are just files that have hashes in them, then it's actually very easy to modify these, which is often a bad thing. So there's an additional type of tag that has a message and then also can be signed cryptographically, and this means that the tag can't be modified because the hash it points to is encoded in the assigned data. But at its simplest level, a tag is literally just that, a pointer. So these are all really the same thing used in different ways. A reference just points to an object. A branch uses a reference to point to a separate stream of development. And a tag is just a ref that doesn't change over time. So again, let's have another low look at this at the file system level. You can do this on your own repositories, create an empty one, do it on your production system. Doesn't matter, it's all there. So we're going to trade the two types here. We're going to create a tag called a tag, and we're going to create a branch called a branch. And we're going to look under Git refs. So the objects are stored under Git/objects. We're going to look under Git refs, which is where it stores all this metadata, these pointers to the system. And if we actually cat is just a way of blasting out, just showing what the contents of a file are. You can see that the branch is literally just that, a hash, as a string stored in a file with the name of the branch. That is how simple Git is. And this is why it's so fast for these low-level operations. You're literally just talking about chucking a bunch of bytes into a file very, very quickly. So this is the core fundamentals of Git. From this, you can pretty much work up to all the higher levels. You can start thinking about other ways of using this. You can actually you can actually abuse it in a lot of ways. So I'm going to talk a little bit about operations on this, including a famous one which caused a lot of trouble. And I'll show you how to get out of this trouble later, but we're going to have a look at reset. You'll probably use reset at some point. This is very useful. It can also get you into a world of hurt. But what is a reset? Reset, essentially, all it does is manipulate a tag for you, or a ref for you. So in the case here, we'll go back. All that the reset does is just move that pointer back down the tree. Now, there's a little bit more to it than that. Reset does a bunch of stuff to the working directory and staging directory. There are a bunch of flags that you can say, I want to keep the current state of the working directory, I want to keep the staging area. There are a few there, but these are implementation details. Its fundamental idea of reset is it manipulates those references for you. Of course, now that we know how this works, we don't actually have to use reset at all. We want to do a reset, we can do it ourselves. What we can do is look up the hash we want to, open up in Vi, Emacs, whatever, that reference file, that branch, and we can modify it directly ourselves. All the Git is doing here is doing that for us. And it does a bunch of extra work by saying, well, we want to destroy data. The hard, all it says is, just completely destroy this and check it out again. But now we can manipulate these things directly. Now, obviously, when you do a reset here, you're moving that tag. That reference, you've overwritten that reference. How do you get back to that previous state? You say you've made a mistake here. You've done a reset. You've moved backwards through your tree. You want to go, oops, I want to go back forwards. Well, despite I'm using the normal convention here in these diagrams, but actually the arrows should go the other way. They all point backwards down the tree to the parent. We only have it's a singly linked list. It's very hard to go back up a singly linked list. You tend to have to go only back through the chain. How do we find out where we were before we did that reset? Well, luckily Git anticipates this and keeps something called a RefLog. RefLog is simply a log of the changes you have made, particularly to references over time. So you add something to a branch and commit it, the branch reference moves, that's entered in a RefLog. We do a reset, that's entered into the RefLog. And we can see that RefLog, and we can go back and work out what we did and what it was previously pointing to and clean it up. And I'll show you how to use that later. One gotcha here, one thing to be aware of, by default, Git only keeps the RefLog for 90 days. So if you're going to screw up, try and screw up and find out about it within 90 days. But within that, this is obviously all configurable as well, but that's just the norm. But 90 days is normally plenty of time to realize. Now, as I pointed out, Git creates a lot of objects as it goes through the system. And a lot of these are often redundant. If I actually add a file and make a change and add a file and make a change and add a file and only then commit, all intermediate versions of that file will have been stored as objects, potentially quite large ones. So how do we keep things clean? How do we stop wasting all this disk space? Well, one of the fundamental insights that Linus had when he was thinking about Git and creating it was that disk space is cheap nowadays, but the programmer's time is expensive. So originally, Git was actually very, very inefficient. It just stored all these objects, and that was pretty much it. However, that's not very good, doesn't work very well, doesn't scale up over time for very large projects or very active ones, and also it's not very efficient over the network as well. So something else needed to be done to make this a little bit more efficient. So I'm going to talk about GC. GC has two concepts behind it, one of which is should be very familiar if you're a Java programmer or really anyone else working in a high-level language, is that GC is just that garbage collection. It finds any objects which are unreferenced and cleans them up. This is very much how garbage collection works in the JVM or any other high-level garbage collected language. Goes around, finds any objects which no longer have references to them, there's no path to them, and then we'll just destroy them. So just to show that again, what we do here is we're going to do a reset, and then we're going to git GC, and that destroys the object. Now, the reason I do prune all there is because I'm forcing the situation. Git will actually keep these objects around for 2 weeks. It gives them a grace period. So it won't just destroy objects every time you do a GC. It will only destroy them after 2 weeks. So you still have the opportunity to go back to the RefLog, even though you've done a git GC. But this is a very, very simple concept, very much the same as the JVM, if you have any familiarity with all garbage collectors in general. The other thing that Git does during a GC is it does a pack. So packs are not something you're generally going to want to worry about. In fact, I almost skipped this part because it's not actually fundamental to Git. Packs are an implementation detail, and they're something that could potentially change over time, and probably will. So a pack file is really the realization that, yes, you can keep all these objects lying around, but it's much better. They're probably going to stay in the same state, the same order, the same chain of events is going to pretty much be immutable over time. You can go back and change history, but you're probably not going to. So what we can do is delta encode this. We can basically say we're going to look at these files, work out what the differences changed, and then only store the changes and not the intermediate states, the redundant information. Now, that is actually how Subversion works at its fundamental level. But it's also one of the weaknesses of Subversion. Have anyone here ever tried to remove a file from a Subversion history? Yeah, a few people. It's a nightmare, isn't it? Bordering on impossible. I end up writing my own tools to try and do it. It's black art stuff. Because it stores differences. If you remove something from the chain, that chain of differences is now broken. You have to know every single chain back through the history. Git is different. Git stores conceptually every one of those intermediate objects. You can actually take these pack files and blow them back up again out to the full object trees and then recompress them. This is why I say pack files may well change over time. They don't generally. But if you can find a new, more efficient pack format that saves 20% or something, great. Just go through your repositories, blow them all out to the full object files, apply the new pack, and you've saved yourself 20%. So this doesn't really affect the conceptual ideas of Git, but it is quite useful to know. So this is just to show you, if we run a GC, and we can go back to our object files, you notice the objects have all disappeared now. And they've been replaced by two files, three actually. One is an index of indexes, a list of the actual pack files. And each pack file consists, in this case, of two files. One is the pack, the raw data, and the other one is the index file, which gives you the metadata about how to find the necessary points for certain files within that pack file. If you've ever done any low-level work with any of the file system-based databases like Berkeley DB, this will probably be quite familiar to you as well. Generally, this is a database concept. You have a data file, and you have an index file that stores how to get to that data in a random access way. The actual internals of the pack file are actually quite interesting. If you're interested in this sort of low-level stuff, I recommend going and have a look at it. It's under the docs directory inside the Git source file. There's lots of information about it on the web. It's very esoteric, and it's written by a very, very smart guy who knows an awful lot about storing information on disk, namely Linus Torvalds. The only documentation on it consists of an email that he wrote up at some point explaining roughly what he was trying to do. It is hyper-optimized for hitting the disk in the most efficient way possible to make it as fast as possible. So it's very esoteric, but if you like a bit of low-level operating systems level hackery or database-style stuff, recommend going and having a look. So that is dealt with the fundamental low-level concepts of Git. Now we're going to talk about some of the higher-level concepts on top of that are necessary to actually turn it into a real version control system. Because we talked about branches, but branches aren't actually an awful lot of use by themselves. And you can go off and work on your wonderful new feature for as long as you like, but if you're going to get that back into the main tree, then what's the use of it? So this is where merges come in. Merges aren't fundamental to the model of Git that I'm talking about here, but they are very, very important in the ideas of on how it actually works in practice, at the slightly higher level of actually turning it into a version control system, being able to collaborate. So what is a merge? At its simple level, a merge is just the point where you converge two branches back together. Very simple. What you have to do, though, is consolidate changes. You have to work out, are there any conflicting changes? If the same file and the same place has been modified by two different people, you have a conflict. If not, you can go ahead and merge, but you want to do so in a coherent way. So Git has a number of different algorithms for doing so, but at its conceptual level, it's also quite simple. It's a merging point. So unlike the point where of a branch where it diverges and you have a parent that has more than one child, a merge, and particularly a merge commit, is a point where you have a child with two parents. So this says, I am in the point of the convergence of these 2 points in time. Now, the fact that this is stored inside the merge commits themselves is quite powerful as well inside Git, because it means you can actually destroy your branches. You can say, I don't want to track these branches anymore, I'm going to throw them away. But this history is still contained. All you've done is throw away the references. And you can actually go back and, through your chain, find the merge commits and find out where the branching points were and work out where the changes were made over time, even if the references to branches have been destroyed. There is one exception to this, though, and Git does do this by default. You probably have heard of the Fastforward merge. This is the simplest form of merge. All this means is you create a branching point, but the main parent has not actually been modified. So why do we have a merge commit at all? We don't have to do a merge because there's nothing to merge. The two are basically equivalent to each other. So all we do is just shift the tag forward, and it's as if nothing happened. Now, this is actually good because it's very, very fast and keeps a clean tree. Unless, of course, you don't want a clean tree. What if you want to keep that history? You don't have those two parents now. You don't actually know that a branch occurred at that point in time. It tells a very clean code story, but it doesn't tell a very clean development story. It doesn't tell you who made the branch, who did the merge, etc. So often, and it's often a question of policy, we will say, no FF. There is a flag during a commit, -- no FF, no fast forward, and it will force a merge commit to be created with the two parents, regardless of whether it's actually required or not. That stores the additional metadata, and it tells a high-level story. Some people want fast forward commits. Some people will go as far as doing elaborate rebases to always keep their tree clean, so that your fast forward you're always going to be fast forwarding. Some other development shops will prefer to keep the true history and will go and go no FF, no fast forward, and always make sure that you're storing where a change came from, including its branching history. So I mentioned there are different merge strategies associated with this. So there are a number of different merge strategies built into Git. The resolve is what you're probably used to if you normal patches. Recursive is what is used in Git by default. This is a fairly new form of merging strategy, and it relies heavily on Git's extensive history. So the idea is that you can go back, and because you can walk back down a tree, you have 2 points where you want to merge, the branch and the branch it came from. You can then walk back down both trees and find out where the shared point was, where the common ancestor is. At that point, you create a bunch of diffs, break it up into chunks, analyze those chunks, and therefore you can find out or make an optimal merge. And you can also do this over complex merges where you've actually had branches and then you've merged, cross-merged branches, carried on working, cross-merged, etc. Git will actually go back and create dummy intermediate merges along the way, and sort of replay a false history for you as well. Very, very powerful. Worth looking into in and of itself if you're interested. But the great thing about Recursive is it generally just works because it's been extensively tested on the Linux kernel. This is the one they use in the Linux kernel by default and in Git by default. Obviously, Linux is one of the most largest software projects in the history of mankind, and one of the most active right now. If it's working for them, it's probably working for you. The other one is Octopus. That's somewhat of a special one where it'll take actual more than 2 branches and actually create any number of branches, take them and merge them into one. Very tricky to do. Generally only used where you have multiple streams of development that are not overlapping and you want to just pull them together. Submodule style systems, so on. We use it for our blog engine because each of our blogs is generally worked on in isolation. So we can just go, all right, pull them all together in one go and then push them out the door. We use it for our staging servers. There's a special merge system called hours. This generally throws away another branch. What it says is, I'm working on feature branch, blah, 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 blah. I go to merge, but what I say, actually forget all that other history. This is now the source of truth. It completely overwrites one branch with another. This is not something you want to do very often, but happens sometimes in long-running projects or long-running branches where the new branch has essentially superseded the previous branch. You're working on version 2.0, version 1 keeps on being created, you're cross-pulling any security fixes, hot fixes and patches and so on. When you get to the end, the release date for your 2.0, that's really, you don't care about one anymore, so you use hours to completely overwrite that history while not actually destroying the history, merely saying we're going to start again from here. Subtree is a powerful one. The closest comparison for a subversion is the subversion externals. That doesn't really quite work like that. It's very useful for pulling in other projects, or if you want to split your project into smaller modules, smaller Git repositories, and then pull them together through a parent one, it's a good solution for that as well. Quite powerful. Quite complex as well. My colleague Nico Paolucci has written about this. If you go and Google Git Subtree, you'll probably hit his article in the top 5 or so. Go read that. He's got great examples of how to use this in practice. The other one is, do we have custom ones? We can actually add custom merge strategies. If we decide that these aren't working for us, we can add our own and plug them in. In particular, it's useful for if you have a proprietary binary format that is actually mergeable, but obviously Git can't merge binary files. There's no idea what the semantic meaning of them are. But if you have some proprietary binary format and you happen to know that you can merge these two files by pulling them apart, looking at the structure, and then merging them back into a new file, then you can add your own merge system in there. So a good example would be if you wanted to merge XML. If people have been overwriting XML and massive changes to it, or you've put your XML into an XML editor and it's completely restructured it, although it's semantically the same, you could actually then have an XML merger that basically breaks it up, walks the tree, finds out if they're the same, and then spits out a brand new XML file that's semantically equivalent to the changes of the both, but looks completely different. So XML is a good example for that. So merge strategies are pluggable. So this is not actually part of the Git core model itself, but it is important to realize what a merge is. The only part of it the Git core is that the fact it has two parents. How it gets to those two parents and the ways of resolving changes between them is a pluggable system that you can use, and you can change at runtime. So while we're talking about merges and so on, we also have to talk about the big elephant in the room, our old friend Rebase. Everyone probably heard of Rebase. Everyone's been told don't do it, or you absolutely have to do it, etc., etc. I will leave that up to your development manager to fight over. The philosophy on this changes quite a lot. But Rebase is actually itself is a very, very simple concept indeed. What we do is we just replay a history at some point, at a different point in time. Now, this isn't the same as, say, a fast-forward merge. It looks a bit like it at the diagram level, but it's not. Because each time we move these files, these commits over time and the objects inside them, we're going to be changing the parent. The parent means the hash changes on that, which means it's now a different object. So we actually have to do a full replay. We can't just move refs around. We actually have to take each commit and replay it as we go along. That's actually a very, very powerful idea in itself, because if you're replaying history, you have a chance to change history. You get a second chance. And we can use that in a lot of quite powerful ways, and I'll show you in a bit. Because we can use some of these ideas that we've talked about so far as a way of getting out of trouble. Does anyone recognize this? I'm just curious. Has anyone seen this? This video? This is the advertisement for the Prince of Persia Sands of Time that was played, I think, in Australia. This is not actually me rewinding this. This is the video. So no one's seen this. All right, this must have been an Australia only thing, or I'm just too old. So we're going to try and use some of the concepts I've introduced now to get out of trouble. This is more than just an academic exercise in, oh, this is Git internals. This is a way of solving your problems by understanding them and realizing that you don't have to know all the commands, you only have to know what commands could exist and you'll generally find them. So we're going to go back to our first one, git reset hard. This is pretty much a rite of passage. So how many people here have done a git reset hard at some point? How many people fucked it up? And you had to go clean the mess up? Right, quite a few. It's a rite of passage. Everyone does this. It's when you, oh yeah, reset, oh yeah, I can get rid of that change. Boom, I have no idea what I'm doing. So how can we use what we know now, our new knowledge, to get us out of this problem? We've done a reset hard, we've now, back in the past, we realized we don't know what our changes are anymore. I can't help you with the actual unstaged working changes. That is anything that was unstaged after reset or reset hard will be blown away, but anything that was inside Git will still be there. So how do we get it back? Well, we know how to do that now because we know that Git doesn't destroy that information. It's tucked it away somewhere very handy for us inside the RefLog. So this gets us out of trouble. We know that we did a reset. We can see it in the log. We actually don't want that reset. We want to get rid of that reset. So we now know that the corresponding previous state was 6cc6637, which is why we're talking refs and not in numbers, because it's not very useful. But we can use that number now and get ourselves out of trouble. So git reset hard, and we just do give it the hash that we want to get back to, and that moves us back to our previous state. So that's a very, very simple idea. And this is the sort of thing that we think about. If we know that reset moves tags and branches and refs around, then we know that we can manipulate them ourselves, and we can fix this. The next one is a favorite of mine. One of my last jobs with my previous team was a massive, massive refactor. I was constantly rebasing, and it was constantly breaking the build, and I found something out only afterwards, which is really, really useful that I'm going to show you now. So you've done a rebase, and you've broken the build. If you've got a long-running branch, you want to rebase it, and to keep it clean, to keep it up to date with the main stream of development. And so we've done a rebase to get it up to date. Unfortunately, something along the way has broken, and you don't know what. One of those commits in that chain that you've replayed has broken the build. What's happened, and what can we do about it? So there's a couple of ways we can do this. One is we can actually replay. We now know that we can use RefLog to get back to the previous state. And then we're going to do a new command, RebaseExec. RebaseExec is a very, very powerful concept. What RebaseExec does is at each point where it replays the history, it'll execute a command for you. If that command returns an error, it will stop. So this is really, really useful. If you want to your rebase is broken, then all you do is run your test suite as part of the rebase after each step on the rebase, and it will stop when you found the issue. So, or where it finds the tests are broken. So that will rapidly find the first step along the way that broke the build. There is also another way of doing this, though. Again, you probably may have heard of Git bisect. Git bisect is very popular with the kernel community. It's not so much used outside, I think, for normal development projects, because ideally you should be running continuous integration and you should find problems out as they happen. However, it is quite useful when you've done something like a rebase or a long stream of development and some errors crept in, you want to find out what it is. Particularly if you can automate the test, but bisect will also work without automation. You can do this manually, or you can do it through automation. What it does, if we jump back, we set a starting point where we know that it is good. The previous good spot. Then we can run bisect, and we can do that make test again. And what bisect will do, will jump to intermediate points and see if the test pass or fail. If it passes, well, it knows the breakage must be further up the tree, so it jumps back to another intermediate point and tries again, and basically narrows down. Now, the good thing about this is I'm using make test here, just as a placeholder for testing, but you can do this manually as well. If this is at some point the PDFs produced by your order system suddenly go all squiffy, then this is a good way to use it. Run it, run bisect. At the intermediate point, Git will stop and say, please mark this as good or bad. You then go off, you run your PDF run or whatever, and look at them. Nope, these ones are good, mark as good. And then Git will mark that as good, find the intermediate point, and then we'll stop again and allow you to check again. So it's a very quickly narrowing down, almost like a sort algorithm to find the intermediate point. Now, I'm getting towards the end here. We actually probably have a little time at the end for questions. But I'll also just do a quick recap. This is the Git data model. This is the entirety of it. All the concepts you need are here. Blobs have content. Trees point to blobs and give them additional metadata. Commits track these changes over time. And commits do that by having parents, possibly with multiple children, possibly with multiple parents. So this is the core of Git, and you can do this. So now we know all this about Git. I recommend going out to your production servers, start mucking around with refs directly and screwing with things. It's great fun. And don't worry, your bosses won't mind that at all. But also you can use this knowledge to help you solve the actual problems you're having on a day-to-day basis. And you can be that guy in that text file who knows the commands, not because he knows the commands, but he knows that the commands must exist because he understands the conceptual model. So hopefully this has been of use to you. We've got a little bit of time, so I'm actually happy to answer questions, or I'll be downstairs on the Atlassian booth for the rest of the day if anyone wants to come and catch me as well. Thank you.